Okay, I welcome you all to this departmental seminar of the Department of Physics, Dhanamanjuri University. Today we have our speaker, Dr. Kshetrimayum Newton Singh. He is an assistant professor at the Department of Physics, NDA, National Defense Academy, Khadagwasla, that is in Pune. So I'll give you a brief introduction about Dr. Kshetrimayum Newton Singh. Dr. Kshetrimayum Newton Singh did his BSc Physics Honours from DM College of Science, from this college. It was from 2006 to 2009. Then he did his MSc Physics from JNU, Jawaharlal Nehru University, New Delhi. And then after his MSc in Physics, he did his PhD from Jadavpur University, Kolkata. And he was awarded the PhD degree in 2022. Currently, he is an assistant professor at NDA, Khadagwasla. And his specializations include theoretical physics, gravitation, astrophysics, cosmology, quantum field theory, many body physics, among others. And his research interests include physics of compact stars, black holes, wormholes, grave star, gravitational waves, Einstein's cluster, general and modified gravity theories, higher dimensional theories of gravity, lead time acceleration of the expansion of the universe. And to his credit, he has published 109 research papers till date, and he has around 3,317 citations. H index is 36 with I-10 index is 76. And currently he is a visiting associate of IUCA, Inter-University Center for Astronomy and Astrophysics, Pune. And in 2019, he received India's top cited author award by the Institute of High Energy Physics, Chinese Academy of Sciences. Again, in 2020, 21, 22, 22, 23, and 23, 24, he was among the world's top 2 scientists by Stanford University and Elsevier. He has a large number of collaborators. He has widespread collaborations all over India and abroad. And currently he is a reviewer in many of the important journals in physics and astrophysics. And at current he is guiding 2 research scholars. So I welcome Dr. Kshetrimayum Newton Singh to kindly present his talk.
Sandali. Sandali. Hey. Sige, full screen na to. Sige. Magi makhongsi. Yaran subscribe. DM College Physics Department ki HOD amadi faculty members ko dimagpu thagatsari. ꯌꯥꯝꯅ ꯀꯨꯏꯔꯕꯒꯤ ꯃꯇꯨꯡꯗ ꯑꯣꯖꯥꯒꯁꯨ ꯊꯦꯡꯅꯖꯔꯦ ꯑꯗꯨꯒ ꯇꯣꯛ ꯑꯃ ꯄꯤꯕꯒꯤ ꯈꯨꯗꯣꯡꯆꯥꯕꯁꯨ ꯃꯌꯥꯝꯗ ꯄꯤꯕꯤꯔꯦ ꯁꯥꯇ꯭ꯔ ꯁꯥꯇ꯭ꯔꯤ ꯑꯅꯧꯕ ꯏꯆꯦ ꯏꯆꯟ ꯃꯈꯩꯁꯨ ꯏꯆꯤꯜ ꯏꯅꯥꯎ ꯃꯈꯩꯁꯨ ꯊꯦꯡꯅꯕꯒꯤ ꯇꯥꯟꯖꯥ ꯑꯃ ꯄꯤꯕꯤꯕꯒꯤꯗꯃꯛ ꯍꯟꯅ ꯍꯟꯅ ꯊꯥꯒꯠꯆꯔꯤ ꯁꯔꯒꯤꯁꯨ ꯃꯇꯝ ꯌꯥꯝ ꯋꯥꯠꯇ꯭ꯔꯦ ꯍꯥꯏ ꯔꯤꯇꯥꯌꯔꯃꯦꯟ ꯇꯧꯕꯒꯤ ꯌꯥꯝꯅ ꯇꯥꯟꯖꯥ ꯆꯥꯅ ꯁꯔꯒ ꯊꯦꯡꯅꯖꯍꯧꯔꯦ ꯑꯗꯨꯒꯤꯗꯃꯛꯇ ꯑꯣꯖꯥꯕꯨ ꯌꯥꯝꯅ ꯍꯟꯅ ꯊꯥꯒꯠꯆꯔꯤ ꯑꯩꯒꯤ ꯇꯣꯛꯁꯤ ꯍꯧꯖꯤꯛ ꯍꯧꯖꯤꯛ ꯒ꯭ꯔꯦꯚꯤꯇꯤꯗ ꯀꯔꯤ ꯃꯇꯥꯡꯗ ꯀꯔꯝꯕ ꯔꯤꯁꯔꯁ ꯇꯧꯔꯤ ꯑꯗꯨꯒꯤ ꯃꯇꯥꯡꯗ ꯈꯤꯇꯪ ꯕ꯭रीफ ꯑꯣꯏꯅ ꯌꯥꯝ ꯗꯤꯇꯦꯜꯗ ꯅꯠꯇꯕꯤꯗ ꯍꯥꯏꯂꯥꯏꯠ ꯑꯣꯏꯅ ꯃꯆꯥ ꯃꯆꯥ ꯈꯤꯇꯪ ꯎꯠꯆꯅꯤꯡꯗꯨꯅ ꯇꯧꯖꯕꯅꯤ ꯑꯩ ꯏꯪꯂꯤꯁꯇ ꯑꯣꯏꯅ ꯄꯤꯖꯒꯦ khidang comfortable agadaw mali. My present talk is on the relativistic astrophysics, the physics of compact star, and black hole, wormhole that everyone have known about in many of the movies and many of the childhood fantasy. And as per the theory of gravity, many things that we have seen in the movies or in the story may have come true theoretically as of now, but we are also expecting to have the proof in the recent future very soon.
Next previous.
So before we start with the beginning of the relativistic astrophysics, I just want to have a highlight on how the origin of the relativistic astrophysics was initiated. First is the Einstein field equation, which was derived in 1915, and Einstein took about 10 years to complete this theory. In 1905, he published the special theory of relativity, and he was very unhappy because that is confined in the constant velocity limit, and most of the systems have no constant velocity, but they have a varying velocity are there, so acceleration must be included. So in last past 10 years from 1905 to 1915, he was extremely unhappy and rigorously asking for the true theory of gravity or true theory of accelerating frames and accelerating objects. So that is how after 10 years he got the field equation. This seems to be a very simple equation, and as per the Einstein's perspective, a good, a beautiful theory equation should be simple. So he thought about this equation before even deriving the equation. So he wrote down this equation and then he confirmed it through several perspectives. So this equation is not a single equation, although it's a 16 differential equation, which are partial differential coupled equation, because this quantities mu nu has indices 4 are there, so there will be 16 differential equations, and they are extremely difficult to solve as of now. And even the supercomputer in the current scientific community also having the challenging to solve this equation as of now. And just after this 1915, Carl Schwarzschild found the first equation, our first solution of the Einstein field equation, which is known as the Schwarzschild solution, or famously known as the black hole solution. And he was one of the scientists in the First World War, and he was calculating in the war field how to solve the Einstein field equation. So he did a very, very beautiful trick that if you choose a symmetry, for example, here in this scenario, he chose spherical symmetry, and he reduced this 16 coupled differential equation into only 4 sets of differential equations where one is irrelevant. So we can definitely say only 3 equations he can reduce. And then he solved for the vacuum solution, which is no matter is there in the outside space. And that is the simplest solution you get, and you can exactly solve by hand without doing anything. Yes, definitely, to come down from the 16 equation to 3 equation, definitely needs a hard work. So this is the first theory of the black hole, and this is the Schwarzschild solution or Schwarzschild's black hole. The second one, in the same paper, it was in 1916, he also find the first, this is the exterior solution or vacuum solution, and this is the interior solution, which is inside an object, maybe inside a star inside a planet or whatever. But yes, this one, it should have extremely heavy mass. Otherwise, general relativity is irrelevant. So this is talking about a huge massive stars. Okay, and this fossil interior solution, he did the same spherical symmetry here. You can see here, this is the two sphere here, and time and space are curved here because of the strong gravity here. And he solved this field equation, again the three differential equation in spherical symmetry, by assuming constant density model, the simplest one of all, because that time there was a first solution and did by hand, so it is an extremely challenging one. So this is a Schwarzschild interior solution, also known as a constant density model. But this gives a very, very beautiful insight in the future. Second one in the 1916 and later on in 1918, because that time nobody knows who did what. So Reissner did in 1916, but unknowingly Nordstrom also did the same thing. So it is now known as the Reissner-Nordstrom metric, or you can say charged black hole. So here in the Schwarzschild only the mass term is there, but in the second term this is a charge term. So if you include a charge into a black hole, then the space-time is also deformed by the charge here. Okay, so this is again having in the Schwarzschild black hole, it has only one horizon at r equal to 2m, but here in the Reissner-Nordstrom solution there are two horizons. Okay, we will not go into the details because the physics behind that thing is a lot of things can be done. Second one, we will not discuss about the cosmological part, but in 1922 and 1935 and 35, separately they did it unknowingly and found the first expanding universe solution, which is the famously known as the Friedmann-Lametrie-Robertson-Walker metric, or FRLW. So this is the one which is giving you the expanding, accelerating universe. So very simple solution, although very, very important one. Then in 1935, Einstein talked about bridge between two distance space area or space-time area where you can connect through like a shortcut. He talked about Einstein-Rosen bridge. It contains one black hole and one white hole. We'll talk about that later on in more details. But the proper title wormhole was given by Wheeler, which is one of the leading teacher who start introducing the general relativity in the graduate level as a special course. And he gave in his seminal work, he gave the name wormhole. And the wormhole, as we talk about now, is given by a very simple metric known as the Morrison-Thorne wormhole. It can be modified a little bit here and there, but more or less the form will be like this. Next, in 1939, again Tolman, Richard Tolman, one of the big guy here in the area, solved the differential equation by hand and discussed 8 exact solutions. Okay, published in one paper, this was in the Physical Review. And unluckily what happened is that only 2 were physically relevant. The remaining are just mathematical solutions. But yes, that time was challenging one. Next, in the same year, Oppenheimer and Serber first found the solution of a neutron star, which is composed of degenerate neutrons only. So he chose non-interacting degenerate neutrons, which give you a Fermi pressure, or you can say Pauli pressure, and counterbalancing the gravity because of the mass. And along with that, he also derived a very famous one called the Tolman-Oppenheimer-Volkov equation, which is simply a hydrostatic equation, the one you did in the fluid dynamics. If you cut out all the extra terms here, which is the general relativistic effect term, then it will be simply giving you the fluid equation, the one we discussed in the pipe flow and everything like that. And what he did is that with that neutron degeneracy equation of state, which is a relationship between pressure and density, they solved the Tolman-Oppenheimer equation, Volkov equation, by hand, numerically, through a calculator, and they found that if a system is composed of neutrons and neutrons only, which are non-interacting Fermi gas, then it should have a maximum mass of 0.7 solar mass only, radius of about 8 kilometers, which is a very, very dense one in the regular scenario. But yes, this was the first thing. So once they did this first mass of a neutron star, everyone was behind it. What will be the maximum or minimum limit of the neutron star? Before that, in the same year as well, this was one of the most productive year in the general relativity. The next one is the Oppenheimer-Sydney collapse. This is a first paper that gives you that a star or stellar system collapsing into a black hole. Okay, the black hole solution was there before, but how the black hole may form, and in this paper, it was the first one to describe a collapsing star, a massive collapsing star can give you a black hole. Okay, so this is a metric behind it. This one is a little bit complicated because this star has to be collapsing, so the solution has to be a time-dependent one. So these are all given in parametric terms. So let's not discuss into it. And this is the simple diagram of collapsing star. So this is a cross-section of the star in two-dimensional form. If it collapses to form a singularity, so this zigzag line here is a singularity. Singularity means what? Ki your everything will be infinite. Either the pressure, density, everything will be meaningless. It will be infinite. So this is also give you the horizon here, which is radius of the black hole, where you can see. Beyond that, you cannot see here. So at the core of the star, it will first compress, and whenever you form a singularity, the center of the star will first form the singularity, and remaining outside particles will infall into that until it becomes and grow into the size of the black hole. Next one is the Budal theorem. It's one of the very interesting one, and this Budal theorem is originated from the interior solution of the Schwarzschild. That is a constant density model of the Schwarzschild second solution, we can say here. And from that, what we come to know is that any compact object which is stable and not collapsing, then the mass by radius should be less than 4 by 9, always. If it is beyond the 4 by 9, it will collapse into a black hole. So very simple one, although still valid. So this was the discussion between the Oppenheimer and the Einstein. This is a solution where he argued that black hole cannot be there. What he assumes is that whenever particle fall into some kind of singularity, instead of falling directly, they will move around in a circular path, making different phases of particles moving layer by layer without colliding each other, and forming some kind of a massive ball-like structure which may behave as a stable object. But the famous Oppenheimer-Snyder paper definitely convinced him that yes, there must be collapse of a star and may form a black hole. Next, in 1963, very far away, this is one of the most complex solution of the Einstein field equation. In the Schwarzschild solution, it was simply static, non-rotating. But if you include rotation, the 16 by 16 matrix of the Einstein field equation will have non-diagonal terms which are coupling to each other. So time radius will be coupling, time theta will be coupling, time phi will be coupling, everything will be coupling here and there. So extremely difficult to solve, but somehow they did it. And this is the rotating black hole solution, which is known as a Roy Kerr or simply Kerr black hole. In the recent observation, I think many of us have seen the picture of the black hole, which was published, I think, few years back in a newspaper. That picture was the first picture given by the Event Horizon Telescope. And it is being found that this solution and the one they observed there is matching. So it's like more or less Einstein's prediction of the black hole, which is a rotating black hole, that is a Kerr black hole, might be correct as of now, as per the current observation. So a very interesting one, although very complex, although it's an exact solution solved by hand. Next one is the Chandrasekhar instability criteria. So when we discuss a compact star, this is very important one, how to initiate a collapse of a stable star. So one of the very famous, very lengthy and very technical paper was given by Chandrasekhar. We talk about this later on. Second one, this is the charged rotating black hole, which is known as the Kerr-Newman black hole, charged as well as rotating. So definitely it's extremely complex. Same metric, except the function delta here will be replaced by a plus q square will be there. Q is the charge of the object. A is the J by M, where J is the spin angular momentum, mass of the black hole. So it's simply known as the spin parameter. Then a very interesting one here, because finding rotating black hole solution is extremely difficult. So Newman and Janis is the PhD student of Newman, and they found out an algorithm which can transform static solution into rotating solution. A very interesting one. You can do any kind of solution here. You can convert from static solution to rotating solution. So if you use the transformation, very complex but not very difficult. Schwarzschild can convert to Kerr, or Reser-Nordstrom, again static solution, can convert to Kerr-Newman solution. Very, very powerful tool here. If you discuss black hole solution, definitely you have to know all these techniques. Then let's go into the compact star, which is, we discuss mostly the neutron star. There are some other star as well. Quark star is there, which is as of now hypothetical star, but there are some small support is there. But let's focus on the neutron star. So how neutron stars are formed? First thing is that the star should be massive. So we call it the main sequence star. Means if the star is burning hydrogen at the core, like our sun, then those are called as the main sequence star. And those main sequence star, if their mass is more than 8 times mass of the solar mass, then they should collapse into neutron star through the famous, fabulous supernova explosion, one of the biggest, brightest object in the entire universe. This was proposed in 1934, but proven later on, because that time the telescope was not very powerful. Then this is a highlight of the neutron star here. The average density is of the order of 10 to the power 15. Okay, and the neutron drift density is 10 to the power 11. Means what? If the density surrounding atom is about 10 to the power 11, then the neutrons from inside the nucleus will be dripping outside the nucleus and coming out from the nucleus. So that density is 10 to the power 11, but the average density of a neutron star is 10 to the power 15, which is denser than nucleus. So that is why in the later slide as well, we will call it as a giant nucleus, because density is more than atom, nucleus. Second one, this is what you call the saturation density. So after this density, the entire particles inside the nucleus, which is proton and neutron, will be seen as single object distributing all around the volume. So there will be no nucleus at all. Next, they are very, very fastly rotating. Okay, they are so fast that their times, the shortest time as of now, which is a PSR means it's a pulsar. Pulsar means it is emitting radio signals like a lighthouse. Okay, so its name is J1748 something something. No, this was given as per the catalog. And the shortest time as of now, the single rotation time will be about 1.34, or you can say 1.4 millisecond. Means it is rotating 716 times a second. Very, very fast rotating. Plus, they are extremely dense, definitely. And the magnetic field strength, you see here, it is 10 power 8 to 10 power 14 times the Earth's magnetic field. Extremely strong. So they are so strong that their spectrum are so polarized that you will be getting a lot of information, and even extracting information is extremely difficult. Plus, density is extremely high. So what are the particles inside the nucleus of the, or core of the neutron, still unknown. So it's a big area of research, either for the high energy physics or for the relativistic astrophysics. So this is the bulk properties. Mass will be, we know the minimum is 0.71, that is the Oppenheimer-Volkov mass. And the maximum mass is yet to explore. That is why we are eager about. So radius will be about 8 to 15 kilometers. Extremely small. So if you take out a spoon and get a spoon of the neutron star, it will be extremely heavy, because density is 10 power 15 order. Central density will be about 4 to 10 times the saturation density, which is of the order of 10 power 14. The compactness means the radius of the neutron star and the radius of the black hole. If you compare it, is only 2 to 4 times bigger than black hole, but the mass is extremely large. The barrier inside, okay, all the protons, neutrons inside will be extremely large number. The binding energy is also definitely very, very large. So you can compare the binding energy here. So the binding energy of the nucleus is of the order of 10% of the rest mass energy of the neutron star, extremely large. So we need massive object, so that is why we did general relativity. And because of the high density, definitely yes, we call it giant nucleus. So these are all the references how we define the solar mass, solar radius. This is the Schwarzschild radius here, because we always compare our radius mass as a solar mass and solar radius. Next is very interesting one. Neutrons are likely superfluid, 95%. And their critical temperature is 10⁻⁹ Kelvin. So in the solid state physics, you can see that people are eager to get a superfluid, and the temperature is extremely low, about maybe 2.7 Kelvin. But this one is high temperature superfluid here. Second one, protons are superconducting. Again, so in the solid state physics superconductor, if you want to get it, you can cool down. I think the highest is around 150 Kelvin or maybe 200 Kelvin, something like that. Okay, but here it's of the order of 10⁻⁹ Kelvin, extremely large. Electrons is very less, it's only 5%. This is to nullify the charge, because every system holds the charge conservation low, so this is to normalize the charge. And the quarks inside the core are also superconducting, color superconducting is there. As of now, it's still discussing and still doing the research, and it has a critical temperature of the order of 10⁻11 Kelvin. Then possibly muons will be there, hyperons, exotica like pion condensation, kaon condensation, etc. There are a lot of things are there. And you can see here, as per the BCS theory, the Burdeen-Cooper-Schrieffer theory, extended to the nuclear physics, definitely, the maximum temperature is about 3.5 MeV. If you convert into Kelvin, it will be about 10⁻⁻ Kelvin. So, a lot of degrees of freedom are there because of many particles coming in, mesonics, quarks, gluons, and what else. Many things can be discovered here. And the properties in this regime, the particles inside will decide what is going to be the maximum mass, depending upon what particles are there. Yes, a lot of things we don't know yet, and still physics are improving. Hyperons will be there, meson condensations will be there, quarks matter, everything will be there, and still questioning about all these things as of now. So, how to go with this? So, it's a very special form here. It's part of the relativistic mean field theory. This is a small portion here, because a lot of things can put in here, but the way you calculate or you do the computation, it will be harder if you keep more and more here. So these are some baryonic spaces, some scalar vector mesons, some isobacter mesons, and the leptons will be there for the charge conservation here. This is simply a model of it, but you can add up a lot of particles are there. Only difficulty will be raising to you. Otherwise, you can put anything whatever you want. So we'll not go into this too much. So now, so this portion is a neutron star. The surface has plasma of hydrogen, helium, ions. Iron nuclei will be there because iron is the last product of the fusion reaction. Outer crust, ions, electron gas is there. Inner crust, heavy ions like iron, ions, everything is there. Electrons are relativistic. Superfluid neutrons are there. And in the outer core, you can see neutrons, protons, muons, electrons are there. And in the inner core, many things are there. So this is not the end, many things are there. This is the one of the old pictures, so not very updated. But at the core, anything is possible. So people are still focusing onto it. And the other side is a strange quark stars, because here in this scenario, the star is smaller than neutron stars, and the pressure of the neutron star is now replaced by strange quark pressure because of degeneracy. Again, quarks are also fermions, so they have Fermi pressure. Again, still, as of now, quark stars are, as of now, hypothetical star, but some of the objects are claimed to be strange stars, but not much. So I think we have seen this in the movie, in the Avenger Infinity War. So you have a place called the Nidavellir, where Thor come to force his Stormbreaker. And he opened the neutron star door, harness the energy, melt the metal, extremely, definitely hard metal, and then he forced the Stormbreaker, the X he is using. And this ring here is some kind of a theoretical ring, or you can say sphere, known as a Dyson sphere, where you can make some kind of a structure around the neutron star and harness the energy from that. Yes, when we have the advanced technology, not as of now. So for massive neutron stars, you need a very, very strong, or you can say stiff equation of states. But for the soft one, we have a lot of equation of states are there. So if you plot the mass versus radius, stiffer will give you more mass, or this softer will give you lesser mass. So if the mass of a neutron is of the order of 10 power 1.4 solar mass, which is nearby about Chandrasekhar limit of a white dwarf, it will be very soft, simple, regular equation of states. But when you go to 1.7 or 1.86 times the mass of the sun, it will also allow little bit. Yes, you can work with them. But when you reach about 2 and above, definitely, what are the particles? How to get those stiff equation of states is still a challenging task. So here, there are very small equation of states, which is the relationship between pressure and density, which gives you the particle content inside a neutron star. They are very limited as of now. So how we incorporate the mass gap neutron star, which means it's a gap between neutron star and a black hole. What is the lightest black hole and what is the heaviest neutron star is what we call the mass gap. In between them, nothing is there as of now. So what is the upper limit of neutron star and what is the lower limit of black hole is called the mass gap, which is in between around 2.5 to 3 solar mass. Very less object has been observed in this area. Okay, look for equation of state which is very stiff. So we are still learning, our knowledge is not yet complete. Or yeah, you can go into an alternative theory of gravity where it can explore or develop a theory which is in parallel with the Einstein or supporting Einstein. They should be stable, otherwise irrelevant, and they should be going along with the observations. So this is a very old one, but I could not get any later version than this. This was published in 2007. The maximum mass in gravity, general relativity is of the order of around 2.5 here. And the remaining equation of state, these names are different matter composition, or you can say the equation of states are there, but only one of them is able to reach up to 2.5 and above. The remaining are very limited here. They are always below 2.5. So they cannot be reaching the black hole neutron star mass gap. Again, this is a catalog of most of the observed well-known neutron stars. So this is the neutron star white dwarf binary stars. Their mass are very less here, about 1.5 K. I mean the up down is there. Again, this is neutron star binary stars, and not very high. Although the mass is around 1.5 solar mass. When you go to the black hole neutron star binary stars, you can go slightly up to some of the high mass here, which might be confusing whether it's a black hole or mass hole. We have no idea. So we are still learning here. So this is very old one. It's called the Hull-Steyler neutron star binary. They got Nobel Prize because this is the first neutron star that measured the mass very, very accurately and also detect indirect confirmation of the gravitational wave, which was predicted by Einstein in 1915. Next, accurately measured neutron star is the Pulsar 0737. Again in 2013, small solar mass here. And from the white dwarf neutron star binary, you can go up to 1.97. This was the heaviest neutron star in 2010. And the next one, this is the next one here. Again, this is the heaviest neutron star in 2013. So the mass is increasing, not very much, but it is increasing as of now. Now, if we go to the next part. So after the gravitational wave observatory in LIGO and Virgo, many black hole neutron star merger, neutron star mergers are there, means they are colliding each other. So you get mass here in the mass gap here, 3.6. We have no idea black hole or neutron star. 2.8 here, 2.1, 2.56, and there are several objects are there. The mass are extremely large. So we are still struggling whether they are neutron star or a very, very light black hole. So again, not fitting well properly with the GR, search for the modified gravity, or you can say alternative gravity. So this is the mass gap here. So here above is the stellar black holes, means black holes formed from the small, stars. Then this is the mass gap here, very few objects are there. Then below here is a neutron star there. Actually, they have not put any kind of objects here, but there are a lot of stars below this. But in between them, very less objects are there. So whatever the mass objects detected between them, still confusing a black hole or a neutron star. So the first thing we want to talk about is the alternative theory of gravity. What happens if we discuss about alternative theory of gravity? So I will not go into details here, just highlight here. So if you take only the first term, this is the Einstein-Hilbert action. Second term is the cosmological constant term, the one you did in the general relativity up to dimension level. Next part is all the possible combination of the curvature tensor here, because they want to go up to the quadratic term here. So this is the curvature tensor's contraction here. So this gives you the Gauss-Bonnet term here, the modified one now, definitely. Then this is a matter term. So if there is a star, that inside a star matters are there. So those matters also have an action. And if you have any additional extra source, we're just putting for the sake of generality, otherwise we can take it out, beta equal to 0, you can cut it out. Okay, so after solving this action by varying the metric tensor, you can get a very complex field equation. Again, this is 16 differential equations. You can reduce to 3 or 4 depending upon your symmetry. Okay, and this tensor is called the Langkos tensor, again one of the most complicated tensor, very difficult to solve. And this Einstein-Gauss-Bonnet theory is not valid below 4 dimensions. As of now, in the special relativity and in the general relativity, you can deal up to 4 dimensions, but in the Einstein-Gauss-Bonnet gravity, you cannot go below 4 dimensions. It should be above 5 dimensions. So now, for simplicity, yes, definitely stars are mostly spherical symmetry. So we talk about spherical symmetry here in d dimension here. We talk about d dimension and we'll put d equal to 1, 3, 4, 5 or whatever, depending upon your dimension. Here we'll be considering 5-dimensional theory, where you take d equal to 5. If you take d equal to 4, it will be 4 dimension, but as I talk about, it is not valid below 4 dimension. So after putting this metric and putting up into 4 to 5 dimension, you can get this complicated differential, the field equation here into 3 sets of differential equation, this one. So this is the time component, this is the radial component, and this is the theta, the angle component is there. The third one is equal to 0, constant is there, so the fourth one, so we generally don't discuss. How to solve it? So we have used, because it's a very complicated differential equation, you can just solve directly. So we choose a technique called the complete geometric decoupling, where these functions here are called the metric functions, which define the gravity. You modify into some kind of 2 functions here. So this chi here and phi here are the decoupling functions, and the remaining a here and x here are the original non-disturbed or unperturbed gravities there, but those are going to modify by the extra source here, because we have put here extra source term here. So beta coupling here is here, So you can see through beta coupling here. If you put beta equal to 0, you can get to unperturbed field equations. So phi and xi are called the geometric decoupling functions. If one of them is 0, then we call it minimal geometric decoupling. So this is the unperturbed system. So here A and X are there. So A and X are here. But if you perturb it, you can get here A transform into A here because we have put chi equal to 0. But here this X will be replaced by H because the function has been modified by the phi coupling parameter here or phi function here. By doing this, we have an advantage here. You can decouple into two field equations. One is the unperturbed, one is the perturbed part. So now, instead of solving the whole thing, which is very difficult, you just solve this separately, and combine together. Okay, so how to combine? This is how we combine. Okay, the time component here, this is the density. 1 component or RR component is the pressure, and this is also the other pressure here. This is the radial pressure, this is the tangential pressure here. So you can find separately, this is the unperturbed system, this is the perturbed part here. So you can put here in this better manner, then you can get the overall solution. How to solve it? First, you take a well-known metric function. So we choose x here, this one. And how to choose it? There's a separate scenario for that. So let's not go into that, otherwise it will be a very lengthy one. So we choose this function, choose a equation of state. This is called the MIT-Beck equation of state, which is giving you a very accurate equation of state for a non-interacting quarks. So all the quarks will be confined inside a spherical hard object, where inside the Beck, the quarks are going to be moving freely without interacting each other. So very, very accurate theory in a very high energy quantum chromodynamics. Then you take a sheet solution. So this is called the sheet solution here. Then you take the equation of state, use the field equations, and then solve it. So using the field equation here, if you take density here, rho, pressure here, P. So if you put here, rho and P that are there, you can solve the other unknown function. But here, you have to solve the perturbed field equation as well. For that, we take another assumption here. This is called the density mimicking. This is called the pressure mimicking. Just a trick to solve the second field equation, which is the perturbed one. So now, after that, you add this thing, you get the overall pressure and density. Then, the interior of the star, there is a space-time inside here, deformed by the mass content, will be smoothly matching with the exterior vacuum. If you don't match it, the space-time will be torn apart, which is not possible. You cannot torn a space-time. So you match with the exterior, this is the interior here, and this is the exterior metric here. So the function here is this one. This was solved by Bauer Desser in 1985, one of the exact solution found in the vacuum in other than the general relativity. But this has two branches. One is asymptotically non-flat. So at far away, if this is the object is there, the planet is there, around the planet, because of the Earth's planet's gravity, the space-time will be deformed. But at far away, space-time has nothing to deform, so the space-time should be flat as per the Minkowski space. So asymptotic flatness will be there, but in this scenario, it is not. If r tends to infinity is there, this goes to infinity. So this one is non-asymptotically flat, but the second branch is asymptotically flat. This is simply the Schwarzschild solution. Okay, so this one is more accurate. So we take only alpha in the positive branch, then you can get this solution, and you can match with the exterior solution, which is the Schwarzschild solution. Pressure. So we are not talking about the radiation. If you talk about the radiation, system will be extremely complicated. So if you take about radiation, you have to think about time part as well. So if you talk about time part, the entire equation will be partial differential coupled equation. So extremely difficult. So forget about the radiation part. We just talk about the sphere with masses or neutrons or any other particles inside. Then at the surface, all those pressure developed by the particles inside has to be 0, because all are under the surface of the neutron star. So pressure should be 0. So from this boundary conditions, matching these two, and then matching the pressure at 0, you can find several constant parameters. This will simplify us that your degrees of freedom will be reduced to simple forms. So this is a diagram here. So this is star. Inside here is the space-time metric, and outside here, this is the Schwarzschild metric in the far away infinity. Okay. Now, if the star should be stable, means non-collapsing, then the gravity which is pulling inside should be counterbalanced by something, okay, which will be definitely the pressure developed by the particles. So it's called the TOB equation, the Tolman-Oppenheimer-Volkov equation. So you balance that. This is the non-perturb TOB equation. This is a perturb TOB equation. So combining together, the system should be heading to 0. This is the gravity force here. This is the pressure term here. This is what we call the anisotropy term, because the pressure in the radial direction, in the transversal direction are generally not equal. So this should be satisfied. Matlab, your force overall should be cancelling each other. Then only you can have a static solution. Next is the boundary criteria, the adiabatic index. So this one is a relativistic adiabatic index. The non-relativistic adiabatic index you discuss in the statistical physics is simply rho by PR. P will be there. Okay, but in the relativistic correction, PR should be there. And for a non-collapsing object, this should be more than 4 by 3. I think this 4 by 3, I think if you do some part of the statistical physics, this is relativistic degenerate electrons adiabatic index is 4 by 3 exactly. 5 by 3 is non-relativistic. So Chandrasekhar take exactly 4 by 3, balance the pressure of the electron, degeneracy pressure, and balance the gravity force, and that is how you get the white dwarf. Okay, but for the non-collapsive object, the adiabatic index 4 by 3 or gamma should be greater than 4 by 3. Otherwise, it will not be enough to hold the gravity, so it will go into collapsing. Next one, this is the Chandrasekhar's consequence. This Chandrasekhar's was more details. You have to disturb the system, generate oscillation into the star, and see how the oscillation evolves. So if the oscillation grows, it will collapse. If the oscillation stops, it will not collapse. Very difficult one. But Harrison, Zeldovich, and Nabokov simplify the thing and simply get if the mass of the neutron star is increasing function of the central density, then it is a stable solution. So the complex Chandrasekhar's always like extremely difficult mathematical problems. Okay, so using this one is much simpler. So we'll be checking mass versus density. The central density should be increasing. So this is the adiabatic index graph. So it is above 2, above 3, above 4, and above 4 here as well. So definitely it's more than 4 by 3. This is the central density versus mass. So all are increasing function. So the solution is stable. So this is the mass radius curve here. Okay, so it can go up to 2 here. Some of them, you can go up to 2 here. It can go up to 2.5. This can go up to 3 here. So this beta is the decoupling parameter we use. This alpha is the Gauss-Bonnet parameter. Again, this is Gauss-Bonnet parameter in different scenario. This is the density mimicking. This is a pressure mimicking. So in the density mimicking, if the decoupling parameter increases by very small amount, say like 0.1, it can go beyond 3 solar mass with a exceptionally good radius here. If it is very large, beyond 16 kilometers, then it is not relevant. But since it is below 15 kilometer, so this mass here, which is above 3 solar mass, now you can get extremely heavy neutron star here in the Einstein Gauss-Bonnet gravity. So this is how we put some of the objects, estimate their radius, not very clear here, but this is the estimation of the radius of the compact stars as per the Einstein Gauss-Bonnet gravity. Next one, this is the new one, FRLMT gravity. In this scenario, this is the extended theory of gravity from the Einstein's one. First, will be the Ricci scalar here. This is a metric from the matter. This is the trace of the matter tensor. And you can modify the function. And you can get a very, let's not go into this, a very complex differential equation. You can say this is a generalized Einstein field equation with so many things are there. And you can choose if you take R, simply GR. If you take R and function of RT, this will be FRT. If you take R plus function of RLM, you get FRLM. This one is very famous one, Starobinsky gravity is there. This can explain acceleration of the universe without including dark energy. So very famous one. This one is also a recent one, energy momentum square gravity. So instead here, LM will be not there. So T will be in terms of quadratic term only here. And this is a consumption equation, which is a TOB equation in a tensor form. So several functions you can take. Let's not go into details. So take spherical symmetry, take a specific form of the function here. Then solve it. These are the TOB equations as per the function. Then you take the equation of state. So this one is a real equation of state. So here you have a slide. It contains neutron, proton, electron, muon in the potential form. Second one is FPS. This is also the same composition but in the variational technique here. APR is again a different one, but it has a higher density range here. In a Togashi, it contains now more lambda and sigma hyperons are there. So depending upon that, you can see slightly different equation of state are there, depending upon how you can change here. So by changing all the interactions here, neutron-neutron here, neutron-neutron as a liquid, neutron-neutron or say 3 neutrons nuclear interactions, if you include that, you can change the equation of states very much. And you got a TOB equation like, the mass radius curve like this. It can go above 2.5, here also slightly above. So by changing the equation of states, the matter composition of the neutron star, you can get all types of observed objects here, and you can definitely see how they are fitting. Next one here, same thing here. It can reach up to 3 solar mass almost. So next one is wormhole, or you can say Einstein-Rosen bridge. So it was originated from the Schwarzschild solution. So they used a technique called the cut and paste. So up to this much is a Schwarzschild black hole with the radius of the Schwarzschild radius. You cut, invert the time, paste into it. You can see some kind of a drum here, and you can see like a wormhole. Definitely it's not travelable because both are black hole, just inverting and cutting and pasting here. But you can see the concept of tunnel inside here. And they even tried to get a particle passing through the wormhole. So this is the famous Einstein-Rosen field solutions, where they try to prevent the singularity, means formation of black hole, and allow to pass particle inside. But this is containing a black hole and a white hole. If the upper side is black hole, then the bottom side will be wormhole. So if a particle go inside this wormhole, black hole here, it will go out as a wormhole in the other side, in the other universe. That is how they did it. But the traversable one, which we can move, we can travel, is the Morrison-Thor wormhole. Very simple one. And how the white holes may be formed, we did a lot of mathematics there, but how they may form was proposed by Stephen Hawking. It might be a black hole in a thermal equilibrium due to time symmetry. You can reverse the time, and if you have a thermal equilibrium, then it may behave like a white hole. It's again theory as of now, not yet observed. So if you take the Eddington-Finkelstein coordinate system, because you cannot say inside a black hole, but to see inside a black hole, you have to change the coordinate system. You have to change the observer. So by changing the observer, you change the time like this and radius like this. This is a very highlight of the simple part of it, so that you can see inside. You can plot a graph here. So these two are exactly same graph, but this one is for the advanced Eddington-Finkelstein coordinate, where if you allow, this is a light cone here, so your light can coming from the past to the future. So because of the structure of the light cone, you see here, when a particle or light is going inside, it will travel inside the black hole and fall into the singularity, the black hole. But if you take the retarded Eddington-Filkison coordinate, you see here, this is the black hole center here, this is the horizon here, this is the event horizon where you cannot see inside. So if you see the light cone here, if a particle goes from the inside, it will follow the light cone into the future and going outside. Okay, so in the black hole, it will go inside the black hole as a one membrane, but in the white hole, from the inside, any particle or any light can go outside the black hole as a one-way membrane, but it can come out. So this is how you get the solution of black hole and the wormhole. So these are simply time symmetry here. So there are certain features are there. The metric here. So this should be finite for finite redshift. So there should be, it should not be infinity. And this also have a specific characteristics. Very simple one. So it should be non-zero finite. And B at the throat should be 0 here because it is constant. And B should be less than, I mean, there are some characteristics that this R naught is the throat of the wormhole. How much is the size of the wormhole? It should be asymptotically flat. So the wormhole solution, when it go away, far away infinity, it should be matching with the Schwarzschild solution. If it is not, then it's not a proper solution. It may contain many of those dark energy particles are there. It should violate the null energy condition, that is the pressure plus density should be less than 0. That is the exotic particle we call it. So here we take a different gravity. Let's not go into details, otherwise it will be hugely mathematical. So we got another gravity called the Kappa-Arty gravity. So here only difference in the gravity, general relativity is that this Kappa-Arty function was simply a g is there, 8 pi g is there, where g is the Newton's gravitational constant. But here that g, instead of taking a constant, we are now taking as a function of the Ricci scalar and the energy momentum tensor stress here, so that we can see how it evolved as a coupling parameter. And for the wormhole metric, this field equation simply get into two equations and a conservation equation here. This is the first time we did. Before that there was no conservation, but as of now here we conserve it. And this is how we take the function in different form and we got a wormhole solution here. So depending upon how much or how the parameter changes, how the wormhole structure changes. So that is how, there are a lot of things are there. I mean, I don't want to highlight here because not very interesting. Graphs are there, but these graphs I think it's good to see. So depending upon how you behave the parameter or how you change the parameter, you can see how the wormhole are changing. Let us skip this part. So these are the pressure, density, everything is there. The next important part is that the average null energy condition. If you want to open a wormhole, a regular matter cannot do it. It should be a specific matter. We call it exotic matter. And those exotic matters should not be at any infinite amount. It should be minimal so that it's reasonable. If it is like infinite amount of dark energy is there, then it's not very physical. But if you use a very minimal amount, then it might be a possible wormhole. So we have to calculate the average null energy condition, which simply gives you this volume integral identifier, we call it. And for the Kappa-Arty gravity, we've got into this form. Then you integrate. Again, this is not integrable exactly. You integrate numerically, and then you plot the graph. So at the throat of the wormhole here, this wormhole throat is of radius 2 kilometers. So here it is vanishing here at the throat. So vanishing average null energy condition gives you that to open the wormhole, you need a very, very small amount of dark energy or exotic matter, which might be physical in the future if we have the ability to control that. This one I'm just giving highlight. After this I will be finishing very soon. So it's called the Graves star. Very interesting one. So this Graves star is a star, but not regular star. Inside is a vacuum supported with dark energy, and outside is a very, very stiff equation here, matter here. We call it gel-Dobbe's fluid. The reason is that it's very stiff is that the speed of sound traveling inside this gel-Dobbe's fluid is exactly equal to the speed of light. So there is no more stiffer, strong equation of state than the gel-Dobbe's fluid. And it is supported by the pressure here, the dark energy pressure. And you can identify here, inside core is dark energy interior, outside shell is the gel-based shell here or gel-based fluid, and outside here it will be exterior space-time will be there, which is Schwarzschild solution, you know that. And we can test a lot of gravity, because in general relativity, existence of gravitar is there. So when we found a new theory of gravity, then all the solutions, the compact star, the wormhole, the black hole, the gravastar, all should be also be countable in the new theory of gravity. So before we proceed anything with the new theory of gravity, you have to see all those things. So when all those things are satisfied, then yes, this theory might be a reasonable theory. So many things can be done in the future. You can put a lot of compact star here with the new theory of gravity. You can test it. You can put rotation, extremely difficult. You can test with cosmological model, because we are extremely now in trouble with expanding universe without any dark energy. Radiations, because stars are always radiating. Or maybe exotic or non-exotic dark matter here, because as of now dark matter is still a big mystery as of now. So these are the few of the works that we have published with our collaborators. Some of them are very good journal, and I think we did good job here. This one I could not touch because I think the time is already finished. A very interesting one. So this Einstein cluster is a very good candidate of a dark matter, where invisible particles are circulating around in a different orbit and different radius, creating a huge bulge of mass which is invisible by any object unless you see through gravity. So one of the strong candidate of the dark matter here. I think there are many references that I have just put only this much only. I think I have more enough there. Adum khangning ba lesu hangbiro interest yauba leibiragadi.
Students in the question, we are inviting questions from the audience students.
Hayeng master ga taw matun loina yaura doni aduna.
Undergraduate students. The PhD student ahum yauri. Wai hope there I MSc student khar yauri. GR over. Maximum the undergraduate. Question yam basic question.
Adum ikai da bida dum hangbiro kesu kai de. Khana bani admane khanbiu.
Discussion never about.
Hangbiro.
Okay, let me introduce him first. He is Devjit. He is Devjit. He just completed MSc 4th semester from Dhanamanjuri University.
Okay.
Master's project MSc 4th semester project He did it on neutron stars. Okay. Neutron stars modeling, equation of state, yes. Comparative analysis. He did some work on that, so I think he wants to ask some questions.
Mass gap is the mass any kind of object. Neutron star ki mass is maximum 2.5 ki niche makhar smile layab ko. Aduga black hole sina 3 solar mass ki mathakta layaba. Kwaidagi yamna pick pa black hole si 3 point something layab ko. Adu kwaidagi lumba, kwaidagi chawba, kwaidagi heavy hoiba neutron star si 2.4 2.5 smile layaba. Ana sigi marak sidane object amta udeba. Habra na object amta udami na mana gap haina kaureba ko. Aduga hauji recently observed ta wada hauji ki marak si gap marak sida object khara ureba ko. An object urei si moina khansanari si neutron star oigadra adu si yamna massive oiba yamna lumba yamna chawba natraga na yamna yangba black hole oigadra haina khansana badu taseng badi ne neutron star dagi black hole lakpagi wari si hauji pawada gyan men tadreba research puri tawri haibabu aduki matik complex oy ko aduna hojiki 2.5 solar mass tagi 3 solar mass phawbagi marakta leiba object ma khaisi neutron star oigadra oiragadi yamna chawba yamna lumba neutron star oiragani black hole oiragana yamna light oiba yamna yangba yamna pikpa black hole oigani aba aduna karambo oidoino adugi discussion tawbagi wane mana leibai maram se nature na pithom bane ba ko yam tang u bane ba ko hojik mamang da 2015 gi mamang am ta uram de ba 2015 gi matung si sida hojik ti event horizon telescope lai do natra LIGO Virgo loin lai ba ko amna observation ma kai si yam khalla technology wang khalla sensitivity hangal lai aduna ne object mayam ama pick up ta wa hore ba pick up ta ho matam sida ano no object sidi kai yam chawina black hole oira neutron star oira khang dre ba hanadi udabgi tumi leramba hojiti loi ukhalamina ne khanuk ta yada ba boundary si kawai da oido neutron star di maximum 2.7 2.9 se 3 makha leini haibung ba natra black hole gi mass to se 3 gi kika mathak smai legadi haibung ba adu khangdo ngai gi neutron star oira black hole oira khangdo ngai gi thabok tu lakchen ba kaima neutron star oira gadi asu am chawba mass se kamai lai do adu adu so muk explain taw do ri ba natte hojiki si kanogi LIGO gi observation sida even yamna weak oiba feeble oiba signal even gravitational wave power detect taw ngami bane ko aduna hojiki sensitivity matang orogadi aduki matik improve oireba ana moina hojik observe tawriba object ma kaisi ayama matam da loina adum more or less adum accurate oira magane ba kikak chena banatana aduna adu kamaina la ino aga general relativity na takpa ngam dragadi kari na tak tore no sini natraga equation of state to koina khangmu wat bagira adugi question ne koina hange se ha solution ji hoju ji research topic ni hoju mass gap ta nang na paper thibiraga di ano mayam la amgani hoju ji question hangi karam mano do hoi nang na equation of state to nang na aina ano ma discover tawre si hapsi la yeng si adu hapsi matam dang sai gi mass ba khedi lo yo khola ba se 2.53 gi maya yo khola ba adu da sigi matter composition se oiba ya na haido ba al hoju paw di ai akoi gi field theory oro high energy physics ki quantum chromodynamics bi oro akoi gi knowledge si hoju paw da hoi phana phana di kano taw improve tawre adu bu research taw de lab tre ba ko auna kari pochi hapsi laga recently kano taw ida na large hadron collider da tetra quark penta quark discover tawri do amada quark hong ta le medana kind of baryons the quark hong ta leba adu large hadron collider last 2 years the 4 quarks leba tetra quarks penta quarks 5 quarks leba on particles create obe lekam nai dere adu kamba particle manung da yauraga mass tu adu yam chawma la ko do adu khangai ge adu research to ba ona particle physics ka adagi general relativity pura mix of fusion area ne anima khang da ya da adu gi
star की matter content
hojiki akoina density ki scale si energy scale si yeng matam da particle ma create tawgi energy si ma minimum ma ki firm energy se yo ga dina density da ram wang ga di sai ki particle do create tawgi chang si am lai re ba amna 10 to the power 15 order la ga di high river particle ma am se loina formation tawgi energy loina phang gare ba hojik si akoina theory na kayumba SCC particle jaur gadi mass sumuk leiba ya akoina high do ne ba sigi pot si akoina observation na utpai wani sumaina mass leiba targadi madur jaur ngod particle di CCC oiba ya sinata gadi oiba ya de exactly kaisu akoina manak chang sila yengudam na ta haiba ngamuro tabudo akoina haiba 2.5 yok targadi chalo CCC jaur mani ma haigumba
concentration highly percentage p particles of different particles were targeting masses ma'am generate
hoi koi gi mana koi gi equation si solve tong matam sida ne particles tongan hapsila ga CMO hapasi amok yengo matang na si hapsilo amok yengo matang amam hapsila sum yeng dore ne ba amam sum yeng matam sida moina khenaba mass khara le ne se amana khidang pige amana khidang chaw amana khidang medium le res man tro comparison tor matung sida percentage to kamaina calculate taw relatively calculate taw bugi wane kam khena ke kya bunu taw mathang kha ka ya do
neutron star decay to where
hoju paw di ma ge lifetime do universal na lo taw da bu yes agar if any environment dagi particle si tasilaba adu oragadi neutron star si quark star form to wi ai hena tasilagadi quark star dagi mo black hole form to wi ai
possibility like
decay to bagi possibility like merger da pokhairaga black hole form to gadi khang de ko
Einstein-Rosen bridge to. Aduga transversal bridge ani main difference kadi.
Einstein-Rosen bridge ta kai da masi one way ne ko black hole da gi changraga wormhole gi side tholok pa ya ba wormhole da gi changraga black hole tholok pa ya de ba Einstein-Rosen ne kai ha da chang thok chang jin ya ba thong mai na
Transversal bridge aduna.
transversal ai duni hojiki Morrison thon wormhole ai se transversal ko ba chatok chen ja ba amuk chalo so hanilak pa ya ba one way two way ba ko two way membrane ko black hole sina one way membrane aduga black hole manung da dum lai kada ba wormhole Einstein-Rosen bridge ha na black hole manung da chango aduga wormhole thoki do ba theory lai ba ko akoi gi black hole si akoi universe black hole oiren khala se ba si black hole si tunnel ama sema aduga atoba universe ama da wormhole oi ba ya ba gi theory am lai maram di si time symmetry yeng matam da sisu ai sanne ba aduna arap jaga ani sidagi changraga tawudi sokan se black hole na khidang di akoi bera di ka ba tara bera ka daga di adu su sat pa ya ba one way da BSc gango su adum hangbi ba ya question am kata lai gera lu gera hangbi ro
I want to know what will one see or experience when they are traveling through a
when they are
traveling through a
wormhole khware lu ri se kamai no udono khang de ba hairi akoina sky sida yenge sky sida wormhole am leram ba wormhole sigi through da akoina yeng matan atoba universe am udori ne ba atoba universe tu ki sky am leram dra moi ki star thopai leram dra ana akoina focus toroga sigi jaga sida si sumba star tho ese koi khang ba kha ba nuti sum yeng am ni na adu nataba atoba star ama thoma ba pattern top ma adu sidi na ma kai mana dena sidi hana leram ba star ma kai do mana dena si atopa jaga gi or ba ya amai khang ne ba koi si even rocket tonga paireng khalo ne somehow accidentally wormhole manung chang ne koi am na khang wa ba na wormhole de thoga atopa universe yo batung da sky cd kai no kai kai star le me am se aduga da khang no ma ade adu tra ga di so khang wa hai hang bi ro gravity se ate ke sunate da kanoni black hole si pam jo mi ma am le ba hojibudi black hole si image ke uram ni na black hole alai rena dum confirm tawre ko nobel prize su ani hom phangare ani phangare adu ahan bana ma comment to da hojiki manungi dark energy si pressure si moi si repulsive pressure le ba ko ona particle si tasin ma taw matam sida ne mapan da gi pressure am na pitholak pasina ne sai tasil laga compact osilaga black hole sem ga da bu seman da bida moina negative energy pressure sina thaktoga black hole seman da gi moina plan to ro mane ba moi gi asem godi moi black hole pam da gi ne ba negative pressure si hoji paw da akoina khangba ngam drit aduna akoina kari kaure exotic particle hai se akoina khangba uba ngam dri ba particle dark energy gumba ana hoji ge dark energy si kari particle oidore no kari pot oidore no hoji paw khang dri am ta universe acceleration to lise aduna ne natra hoji paw ka su ka im da khang dri dark energy matang da research area ne biro adum yare string theory ahan bagi matung ina 26 dimension lege dabni adu string theories ma ke harau de ba so am yam lege di ka bai deal tawdai no ta aduna onsil laga kuptharaga merge tawraga dimension 11 ba wodi hojik m theory ta is dimension 11 dagi di hen drena hoji pawgi matung ina aduna adu dagi helaga di physical ordena laure hoi theory si mayam am leiri magi kare ni research to finding du matung ina singularity na energy drive toroga tawune habasu lei natraga black hole lagi expand toroga kai mayam lei ko adu ꯍꯧꯖꯤꯛ ꯐꯥꯎꯕꯒꯤ ꯑꯣꯏꯅꯗꯤ ꯃꯌꯥꯝꯅ ꯁꯞꯄꯣꯔꯠ ꯇꯧꯕꯗ ꯗꯥꯔꯛ ꯑꯦꯅꯔꯖꯤꯒꯤ ꯃꯇꯥꯡꯁꯤꯗ ꯁꯞꯄꯣꯔꯠꯇꯤ ꯇꯧꯕꯤꯔꯤ ꯑꯗꯨꯕꯨ ꯗꯥꯔꯛ ꯑꯦꯅꯔꯖꯤꯁꯨ ꯄ꯭ꯔꯣꯕ꯭ꯂꯦꯝ ꯂꯩꯔꯤꯕꯅꯤꯅ ꯑꯗꯨꯝ ꯌꯥꯅ ꯌꯥꯅꯕ ꯂꯩꯔꯤ ꯍꯥꯏꯇꯥꯔꯦ.
Let me introduce the speaker. Student, he just completed his MSc 4th semester. Magi MSc project ki koi Rainer West ki supernova type 1 is standard candles in accelerated expansion of the universe. Adi cosmological modeling to. Adu magi to gi bane ba. Aduna super type 1 is supernova data to analysis fitting to ika. Aduga 70% kya na pang gibla. Dark energy 70% pang gina tra. Aduga adudagi base of.
ꯑꯗꯨꯅ ꯑꯩꯈꯣꯏꯅ ꯗꯥꯔꯛ ꯑꯦꯅꯔꯖꯤꯁꯤ ꯌꯥꯎꯗ꯭ꯔꯤꯉꯩꯗꯃꯛꯇ ꯑꯇꯣꯞꯄ ꯒ꯭ꯔꯦꯚꯤꯇꯤ ꯑꯃ ꯌꯦꯡꯕꯒꯤ ꯋꯥꯅꯤ. ꯑꯗꯨꯗ FRLMTꯒꯁꯤ ꯃꯣꯏ ꯗꯥꯔꯛ ꯑꯦꯅꯔꯖꯤ ꯌꯥꯎꯗꯕꯤꯗ ꯑꯦꯅꯔꯖꯤ ꯑꯦꯛꯁꯄꯥꯟ ꯇꯧꯍꯟꯕ ꯌꯥꯏ. ꯉꯁꯥꯏꯒꯤ ꯃꯣꯏꯒꯤ ꯐꯪꯁꯟꯗꯨ ꯁ꯭ꯄꯦꯁꯤꯐꯤꯛ ꯐꯣꯔꯝ ꯂꯧꯔꯒ ꯑꯗꯨꯁꯨ ꯚꯦꯔꯤꯐꯥꯏ ꯇꯧꯒꯗꯕ ꯌꯥꯝ ꯀꯨꯏꯅ ꯆꯪꯒꯗꯧꯔꯤꯅꯤ. ꯑꯇꯣꯞꯄ ꯂꯩꯕꯤꯔꯤꯕ꯭ꯔꯥ? ꯃꯌꯥꯝ ꯌꯥꯈ꯭ꯔꯦ. ꯑꯩꯈꯣꯏꯅ ꯎꯕ ꯉꯝꯗꯕ ꯃꯔꯨꯑꯣꯏꯅ ꯕ꯭ꯂꯦꯛ ꯍꯣꯜꯁꯤ ꯎꯕ ꯁꯨꯡꯉꯝ ꯉꯝꯗ꯭ꯔꯦ. ꯍꯧꯖꯤꯛꯄꯨꯗꯤ ꯏꯚꯦꯟ ꯍꯣꯔꯥꯏꯖꯟ ꯇꯦꯂꯦꯁꯀꯣꯞ ꯂꯥꯛꯄꯗꯒꯤ ꯈꯔ ꯎꯕ ꯐꯪꯉꯦꯗ. ꯑꯗꯨ ꯐꯪꯗꯕꯤꯗ ꯌꯥꯝ ꯂꯥꯞꯈꯤꯕ ꯑꯣꯕꯖꯦꯛ ꯎꯕ ꯐꯪꯗꯕ ꯃꯌꯥꯝ ꯑꯃ ꯂꯩꯔꯤꯁꯤ ꯂꯥꯏꯒꯣꯒꯤ ꯃꯥꯒꯤ ꯁꯦꯟꯁꯤꯇꯤꯚꯤꯇꯤꯒꯤ ꯂꯦꯚꯦꯜꯁꯤ ꯑꯗꯨꯝ ꯏꯝꯄ꯭ꯔꯨꯞ ꯇꯧꯈꯠꯂꯛꯑꯦꯕꯀꯣ. ꯑꯗꯨ ꯇꯧꯈꯠꯂꯛꯑꯕꯅꯤꯅ ꯕ꯭ꯂꯦꯛ ꯍꯣꯜꯗꯨ ꯎꯕ ꯉꯝꯗ꯭ꯔꯒꯁꯨ ꯃꯥꯒꯤ ꯃꯔꯖꯔꯒꯨꯝꯕꯗ ꯊꯣꯛꯂꯛꯈꯤꯕ ꯕꯥꯏ ꯄ꯭ꯔꯗꯛ ꯍꯥꯏꯇꯥꯔꯦ ꯒ꯭ꯔꯦꯚꯤꯇꯦꯁꯅꯦꯜ ꯋꯦꯕꯁꯤ ꯁꯤ ꯎꯔꯒ ꯕ꯭ꯂꯦꯛ ꯍꯣꯜꯒꯤ ꯏꯚꯣꯂꯨꯁꯟ ꯀꯃꯥꯏꯅ ꯇꯧꯕ ꯍꯥꯏꯕꯅꯆꯤꯡꯕꯁꯤ ꯑꯁꯤ ꯃꯇꯥꯡꯗ ꯗꯤꯁꯀꯁ ꯑꯗꯨ ꯃꯉꯥꯏꯔꯦ ꯑꯩꯈꯣꯏꯅ ꯍꯧꯖꯤꯛ ꯍꯥꯏꯕꯕꯨ. ꯑꯗꯨ ꯒ꯭ꯔꯦꯚꯤꯇꯦꯁꯅꯦꯜ ꯋꯦꯕꯀꯤ ꯃꯥꯒꯤ ꯀꯔꯤ ꯍꯥꯏꯅꯤ ꯐ꯭ꯌꯨꯆꯔ ꯍꯥꯏꯔꯒꯗꯤ ꯑꯩꯈꯣꯏ ꯍꯦꯟꯅ ꯑꯣꯕꯖꯦꯛ ꯃꯌꯥꯝ ꯑꯃ ꯑꯣꯕꯖꯥꯔꯕ ꯇꯧꯔꯒ ꯍꯦꯟꯅ ꯑꯅꯧꯕ ꯐꯤꯖꯤꯛꯁ ꯃꯌꯥꯝ ꯑꯃ ꯑꯦꯛꯁꯄ꯭ꯂꯣꯔ ꯇꯧꯕꯒꯤ ꯄ꯭ꯂꯥꯟꯅꯤ ꯇꯧꯔꯤꯁꯦ. ꯃꯥꯁꯀ ꯔꯦꯗꯤꯌꯁꯀ ꯈꯪꯒꯅꯤ, ꯑꯇꯩꯗꯤ ꯀꯥ ꯍꯦꯟꯅ ꯈꯪꯕ ꯉꯝꯃꯣꯏ. ꯑꯗꯨꯅ ꯑꯩꯈꯣꯏꯅ ꯃꯣꯏꯅ ꯀꯩꯅꯣ ꯇꯧꯋꯤꯗꯅ ꯀꯔꯤ ꯍꯥꯏꯅꯤ ꯋꯦꯕꯁꯤ ꯂꯥꯛꯑꯦ, ꯑꯣꯕꯖꯥꯔꯕꯦꯁꯟ ꯑꯃ ꯂꯩꯔꯦ. ꯑꯗꯨꯒꯤ ꯋꯦꯕꯁꯤꯒ ꯃꯣꯏꯅ ꯁꯣꯝꯀꯥꯟꯗ ꯑꯥꯏꯟꯁꯇꯥꯏꯟꯒꯤ ꯐꯤꯜ ꯏꯀ꯭ꯋꯦꯁꯟꯁꯤ ꯅ꯭ꯌꯨꯃꯦꯔꯤꯀꯦꯜꯂꯤ ꯁꯣꯜꯕ ꯇꯧꯗꯣꯔꯤꯅꯦꯕꯀꯣ. ꯑꯗꯣ ꯃꯣꯏꯅ ꯃꯥꯁꯁꯤ ꯍꯥꯞꯆꯤꯜꯂꯦꯕ. ꯁꯦ M1 ꯁꯨꯃꯥꯏꯅ ꯄꯤꯔꯦ, M2 ꯁꯨꯃꯥꯏꯅ ꯄꯤꯔꯦ. ꯑꯗꯨꯒ ꯋꯦꯕ ꯑꯃ ꯖꯦꯅꯦꯔꯦꯠ ꯇꯧꯍꯜꯂꯧꯕ. ꯑꯗꯨꯒꯤ ꯋꯦꯕꯇꯨ ꯑꯅꯤꯗꯨ ꯑꯃꯅ ꯑꯣꯕꯖꯥꯔꯕ ꯇꯧꯒꯅꯤ, ꯑꯃꯅ ꯊꯤꯑꯣꯔꯤꯒꯤ ꯋꯦꯕꯅꯦꯕ. ꯑꯅꯤꯁꯤ ꯑꯣꯚꯔꯂꯦꯞ ꯇꯧꯗꯣꯔꯤꯅꯦꯕ. ꯑꯗꯨ ꯄꯔꯐꯦꯛꯂꯤ ꯑꯣꯚꯔꯂꯦꯞ ꯇꯧꯔꯕ ꯑꯗꯨꯑꯣꯏꯗꯤ ꯁꯤꯗꯤ ꯕ꯭ꯂꯦꯛ ꯍꯣꯜ 5 ꯁꯣꯂꯔ ꯃꯥꯁꯀꯤ ꯕ꯭ꯂꯦꯛ ꯍꯣꯜ ꯑꯃꯒ 1.5 ꯃꯥꯁꯀꯤ ꯅ꯭ꯌꯨꯇ꯭ꯔꯣꯟ ꯁ꯭ꯇꯥꯔ ꯑꯃꯒ ꯃꯣꯏꯒꯤ ꯋꯦꯕꯁꯤ ꯃꯔꯖ ꯇꯧꯔꯦ, ꯑꯦꯛꯖꯦꯛꯂꯤ ꯑꯣꯚꯔꯂꯦꯞ ꯇꯧꯔꯦ. ꯑꯗꯨꯑꯣꯏꯗꯤ ꯑꯅꯤꯗꯨꯒꯤ ꯃꯔꯖꯔ ꯑꯣꯏꯔꯝꯒꯅꯤꯅ ꯑꯗꯨꯃꯥꯏꯅ ꯈꯪꯕ. ꯑꯗꯨ ꯀꯔꯤꯒꯨꯝꯕ ꯅꯪꯅ ꯈꯤꯀꯥ ꯈꯦꯠꯅꯔꯕ ꯑꯗꯨ ꯑꯣꯏꯔꯒꯗꯤ ꯖꯒꯥ ꯈꯔ ꯃꯦꯆꯤꯡ ꯇꯧꯕ ꯌꯥꯏꯀꯣ ꯃꯣꯏ ꯒ꯭ꯔꯥꯐꯇ. ꯑꯗꯨ ꯑꯌꯥꯝꯕ ꯖꯒꯥꯗꯤ ꯃꯦꯆꯤꯡ ꯇꯧꯔꯔꯣꯏꯕ. ꯑꯗꯨ ꯃꯦꯠꯆ ꯇꯧꯔꯒꯗꯤ ꯉꯁꯥꯏꯒꯤ ꯅꯪꯅ ꯍꯥꯞꯆꯤꯜꯂꯨꯔꯤꯕ ꯃꯥꯁ ꯑꯅꯤꯗꯨ ꯂꯥꯜꯂꯦ ꯍꯥꯏꯗꯣꯔꯤꯕ. ꯑꯗꯨꯅ ꯇ꯭ꯌꯨꯟ ꯇꯧꯔꯒ ꯃꯥꯁꯇꯨ ꯃꯣꯏꯅ ꯃꯦꯆꯤꯡ ꯇꯧꯔꯒ ꯁꯤꯒꯤ ꯃꯥꯁ ꯑꯅꯤꯁꯤꯗ ꯑꯅꯤꯁꯤ ꯒ꯭ꯔꯥꯐ ꯑꯅꯤꯁꯤ ꯃꯦꯆꯤꯡ ꯇꯧꯔꯦ ꯍꯥꯏꯕ ꯃꯇꯝꯗ ꯑꯗꯨꯗꯤ ꯕ꯭ꯂꯦꯛ ꯍꯣꯜ ꯑꯃꯒ ꯅ꯭ꯌꯨꯇ꯭ꯔꯣꯟ ꯁ꯭ꯇꯥꯔ ꯑꯃꯒꯤ ꯃꯥꯁ ꯁꯨꯛ ꯑꯅꯤꯗꯨꯒꯤ ꯃꯔꯖꯔꯅꯤ ꯈꯪꯕꯒꯤ ꯋꯥꯅꯤ. ꯌꯥꯕꯤꯅꯤꯡꯉꯕ꯭ꯔꯥ?
Yeah, any question?
ꯑꯗꯨꯝ ꯍꯪꯕꯤꯌꯣ, ꯍꯌꯦꯡ ꯐ꯭ꯌꯨꯆꯔꯗ ꯑꯗꯨꯝ ꯃꯁꯇꯔ ꯇꯧꯒꯗꯕꯅꯤꯅꯅꯦ. ꯂꯩꯇꯕ ꯃꯥꯜꯂꯦ ꯑꯩꯒꯤ ꯋꯥꯈꯜꯗ.
ꯈꯪꯕ ꯕꯦꯁ ꯂꯦꯚꯦꯜꯗꯤ ꯅꯠꯇ꯭ꯔꯥ?
ꯍꯣꯏ.
ꯍꯪꯒꯗꯧꯁꯦ ꯀꯗꯥꯏꯗ ꯍꯪꯗꯣꯏꯅꯣ ꯈꯪꯗ꯭ꯔꯦ.
ꯖꯦꯂꯣꯕꯤꯁꯀꯤ ꯃꯇꯥꯡ ꯀꯔꯤ? ꯖꯦꯂꯣꯕꯤꯁ ꯐ꯭ꯂꯨꯏꯗꯁꯤ ꯑꯁꯦꯡꯕꯗꯤꯅꯦ ꯀꯩꯅꯣꯒꯤ ꯀꯣꯁꯃꯣꯂꯣꯖꯤꯀꯦꯜ ꯃꯣꯗꯦꯜꯗ ꯗꯤꯁꯀꯁ ꯇꯧꯕꯅꯦꯕꯀꯣ. ꯀꯥ ꯍꯦꯟꯅ ꯔꯤꯂꯤꯚꯦꯟ ꯑꯣꯏꯗꯦꯕ. ꯃꯔꯝꯗꯤ ꯑꯦꯅꯤ ꯃꯦꯇꯔ ꯗ ꯁ꯭ꯄꯤड ꯑꯣꯐ ꯁꯥꯎꯟꯁꯤ ꯂꯥꯏꯠꯀꯤ ꯁ꯭ꯄꯤꯗꯀ ꯆꯞ ꯃꯥꯟꯅꯅ ꯆꯠꯄ ꯃꯤꯗꯤꯌꯝꯁꯤ ꯑꯝꯇ ꯂꯩꯇꯦꯕ. ꯑꯗꯨꯅ ꯈ꯭ꯋꯥꯏꯗꯒꯤ ꯌꯥꯝꯅ ꯊꯤꯑꯣꯔꯤꯇꯤꯀꯦꯜꯂꯤ ꯁ꯭ꯇꯤꯞ ꯑꯣꯏꯕ ꯌꯥꯝꯅ ꯀꯟꯕ ꯏꯀ꯭ꯋꯦꯁꯟ ꯑꯣꯐ ꯁ꯭ꯇꯦꯠ ꯍꯥꯏꯔꯒꯗꯤ ꯖꯦꯂꯣꯕꯤꯁ ꯁꯤ ꯈꯛꯇꯅꯦꯕ ꯑꯦज ꯑ ꯊꯤꯑꯣꯔꯤꯀꯦꯜ ꯃꯣꯗꯦꯜꯅꯤ. ꯑꯗꯨ ꯅꯠꯇꯕ ꯑꯇꯣꯞꯄ ꯑꯦꯛꯖꯦꯛꯂꯤ ꯐꯤꯖꯤꯀꯦꯜꯗ ꯀꯔꯤ ꯄꯣꯠ ꯑꯣꯏꯒꯗꯧꯔꯤꯅꯣ ꯍꯥꯏꯁꯤ ꯈꯪꯗꯦꯕ. ꯑꯗꯨꯕु theoretical limit की मतुंग इना speed of sound सी light की speed तक हेना चलते याद है मरम दी causality hold तो वदा बने light की speed से maximum speed है ना ट्रा और ना light की हेन में याद है ना p equal to rho है मतलब सीधा light की speed का light sound की speed का चम आने है अदुना अदु की दो ओएगा दी आई दी universe की evolution कमाइन तो गुनी ना ट्रा star कमाइन तो गुनी है ना मोना theoretically discuss तो बगी वाक़ करते हैं physically किधंग irrelevant हुए criteria ammonia lobo yade adubu as a physical particle oina speed of sound gi tagadaba adu tadragadi adudagi hengergadi kari particle no khangde maramdi Einstein gi general relativity special relativity matungena speed of sound is a maximum limit speed of light is a maximum limit aduna adudagi tadragadi yade adudagi tadragadi kari pot no haidu khangde ba Hoje kanogi tachyon ka lay disi. CDMO again theoretical particle ni duna loksin ba yate hoje pauti. Habiro. Ha. Moi gi sina kidang experimental ore ko moi gi high energy physics matang sida. Moina particle si hanagi large hadron collider ki energy si moina increase to mane ba koi gi update to matung sida moi chai ga update to ko moina taliba target si phanayam wang moi energy si adu energy si ahamba bapu kayani se 25 GB da run to mane mathang chai da amuk se 30 GB da run to do ne ba aduga proton smashing to mo tam sida kari energy si hangat pa matam da kari particle lak pa du yeng mane ba adu yeng matam da kwak ahum punba baryons paudi akoina khange adubu kwak mari punba kwak manga punba su yoksilakpa anuwa particle se ana moisi koi gi particle physics nei ne standard model nei da bane ba hojiki haiba particle makai si beyond the standard model ne ba aduna nangna particle anuwa puthobani na theory su anuwa puthokta yadre awna hojik particle yang kholai matik physics su yang kholakta riba aduna adusu moi kanguna research ko high energy physics to kanguna adu research to detect to haibu theory hoj bo sem dre ba moi khara dik thabak to ngani yaro malai wa kala
Any other question?
Yeah, Shira.
yum chane ngaba male
So let us thank the speaker once again. Thank you, Dr. Newton. And fortunately for us, he is an alumnus of the College of Science. Okay. Aduna, so today is not the last. We will continue having many discussions, offline, online. Okay. So the basics में हम लोग brush up करो, and in the next session call, maybe some few months back or 2 months later or anytime, you can ask more questions.
Yoga sigi batang da research ko ni bela ni da project ko just layer ka de ki su project हमने जरूर लिखी
Yes.
और मैं रिफर तो sana seriously on research to complete
Thank you. At present, we have 3 students who are actually GR as a research topic. GR field theory. So we mainly work in working radiation from levels. So we did work mainly on third dimension levels. So working radiation as an energy. So we get so freshman lah. Sorry. Speaker say thank you high boy enough. Gratitude. कोई साथ ऐसा नहीं है बिना वास्तव में
Kari haidu ko diko penuni akhui saturni na khu muni rongsi di pura manasu wari singse pura ka koi se atop dilemma atop dimension ma da pugudon towi atop sankharam da koi tau re tau bidan te tingau re adu aidi amaron da manasu na toni re se faziru di isu pinge di culture to ga toina gi bunina ai mitadi angang winu budi ana mama mapa na masana jagoi sa uraga sari jagoi do kadai de soige khang do goi maga tu le masagi tindu de dum yaw do do just chap mana re arna aina haning di mana pdb inspiration khudi mak chei na khoi su dum lo na no khono loina na I feel proud to be the teacher of this no resource person orisi adu ai ma bu khoi gi satro ibigi ko yamna kaitare se I nungai jaba masu feel tawi at the same time I have the privilege to be a proud teacher of him sima de ai haininge adu ko aina su am toina hai gi bani adu gi challenge amada ma to gi bari khang de na khoi gum na to gi matam da di ai ngon na hangning ba mayam ma lai ai na hai yobam tam na hang ngam de to dro nang bo kari gi nu khang de ai mong na kai mok sai de hangning ba lai adum ai na hai ga ma to min adum chakhini ko ai na hai Manipur University da tambada phatte hai banate adu you need to expose atopa atmosphere ma da expose to ga di nang ngang ni ba du bok ti yong na ba ngang ngam dong mali adu hai ba ga to ba ga ma Jan University da du gi chai du mak ta da dum phangi adu ma tu na gi de ko kuire after long gap ai ngasi u ma tam da di mana puri ba magi ai di rather some emotional oire ba magi personality ani gi amna depart to ba adu gu ma keno do madun ai pora kai tare se feel proud to be his teacher and hai tare ko okay matung na su ko any nangi eventuality then adagi kahetare chana ba tanjala agasu ko where welcome you anytime ko matam da hena na khoi su sa better interaction pb anana ba ko thim do hanati kitang tele matam se khoi na su da khoi da highlight to matam do yam low hidre maram de we have lot of commitment departmental work me am lei gre ba ko matung na di chance phang ga di am the prior na khoi inform tor ke aduga area keno do interaction do hena nungai na ba ko na khoi readiness lairo okay namangolo yu ko
ma generate tore na haidana adugi matang da haipe habiu ba
star oina koi gi hydrogen burning star main sequence star oina lai matam sidane ngasai gi temperature sina yam wang bana maram oduna gas ma kaisi ionized organ lay ko aduga magi gravity da maram oduna ngasai gi gas ma kaisi chumna laite ba unga lay ko na unga lay bagi charge ion ma kai unga lay rabni na karena ma chela mina magnetic field ma lay rane ba ko aduna magi yam top magun ama hare ga dina ngasai gi star hydrogen burning star na lay matam sida lay ba magnetic field se asi magi entire cycle of the evolution sida amukta ta deba yam chawring sida magnetic field do se 1 gauss kumba lairen khalo adugi 1 gauss to kilometer se kalani desing taruk tere chaw le ngodori ne ko adudagi henna adugi same gravity magnetic field do pixel laga 10 kilometer radius ta confine tromatam langa sai gi magi magnetic field do adugi wa ka ki ne sibu kai ka flux conservation law ka ba hana lairamba chawring lairamba magi magnetic field do physics pela kan su chamana laibagi strength magi flux density wa khalak bai tar no flux density wa ngamina magi magnetic field yang wa and newly born star yorga di moi di highly 10 to the power 15 gauss ka lairese aduga moi si adugi matik fast ungbagi chang si sida moi si radio waves thadoi ne radio waves aduga moi gi spin si adugi matik regular obi chang si moi si kari hane kaubi natural clock haina khangne ba maram di clock haira di gari yam tik tik taw yam phajana regular taw du reka afaba clock kawi dana adumaina akoi gi rotating neutron sa sibu kari hane khangne natural occurring or natural clocks hana su khangne ba adugi matik regular oi ba ya birabra